Okay, Assalamualaikum warahmatullahi wabarakatuh. So we're going to continue with a single phase full wave uncontrolled rectifier, and this is a session again the session's outcome, right? So after this session, inshallah, you'll be going to be able to describe the operation of the rectifier, which is the full wave control rectifier. You'll be able to derive the quantities related to performance of the rectifier. You'll be able to solve problems related to the rectifier, and finally you'll be able to simulate the circuit itself using PCIN. Okay, let's go straight to the model graph. That will be under chapter 5, which is 5.3. We know that give me a second, so I want to activate the okay, so now we are on the 5.3, okay, which is single phase full wave control rectifier. So again, inshallah, you'll be able to understand it quite easily, because this is just an extension of the full wave uncontrolled rectifier. Uncontrolled because we use a diode. It is a control rectifier because you utilize the thyristors. Okay, now you utilize thyristors. So again, as what you did for the full wave uncontrolled rectifier, we're going to add another 3 thyristors, right? And namely T2, T3, and we have T4 there. Okay, so for the diode operations, the diagonal thyristors will be operating at the same simultaneously, right? They will be operating in the same times, and we have this T1 and T2, the first diagonal switches, pair of switches, and then we have another pair of T1, T3 and T4. Okay, so in terms of the firing angle, you're going to supply the same pulse, the same gate signals to the diagonal diode, right? So for example, if we look at this, circuit, PCIM circuit, you're going to have 45, 46, and for T2 also we're going to have 45, 46, and for the other pair of diagonal thyristors, which is T3 and T4, you're going to add another 180 degree to the alpha. So here you're going to add 180 degree plus the value of alpha that you have for T1 and T2. So for this example, you're going to see that you're going to have 225, whereby 180 degree plus 45. So you're going to have 225, and again this 226 is actually because we have a short pulse, isn't it? All right, so that's mainly the how we're going to construct the circuit. Okay, so in terms of the waveforms, it will operate again if you understand the single phase uncontrolled rectifier. If I can go back to the single phase uncontrolled rectifier here, click there for resistive load, right? So during positive half cycle, the diode 1 and diode 2 will be forward bias, isn't it? And D3, D4 will experience a reverse bias, and therefore D1, D2 will conduct, conduct at 0 point here, 0 degree, 0 seconds. So D1 and D2 will operate, and therefore this voltage will be equals to the supply voltage. So it will copy exactly as the same supply voltage. However, during the negative half cycles, D3 and D4 operate. Sorry, D3 and D4 operate. Now the current will flow through this point, that point, sorry, and therefore you're going to see that your output voltage will be the mirror image, the opposite to the supply voltage here. So that's why you have for full wave uncontrolled rectifier, you're going to have this full wave output voltage waveform there, whereby in one cycle you're going to have 2 pulses. Okay, in one main cycle you're going to see 2 pulses of the output voltage. voltage. Okay, so therefore if you replace this D1 and D all the diodes here with thyristors, you only actually delay the turn on, isn't it? You only delay the turn on, and it depends on the value of firing angle. And we only define the alpha for the firing angle for T1 and T2. So let's go back to the resistive load here. All right. Okay. So therefore, during positive half cycle, we're going to see that T1 and T4 will experience a forward bias, but it still wait for alpha, the firing angle, the gate signal to be triggered. And once the gate signals have been triggered at alpha, then we're going to see that T1 and T2 will be switched on, and therefore the output voltage will copy the supply voltage. And that's why we have this output voltage waveform just after the alpha here, isn't it? Just after alpha, then we see this voltage waveform. Right? What happens during negative half cycles? So during negative half cycles, T1 and T2 will experience a reverse bias, and therefore, and because of we have a output purely resistive load, and therefore the current start to flow in the opposite direction of T1 and T2. Therefore, T1 and T2 will appear as a open circuit. This is open circuit. Now T3 and T4 will be turned on. Okay, so when that's happened, I mean not turned on yet, but it's still, I mean it's experience a forward bias, and therefore we have alpha plus 180 degrees, isn't it? So once it reach alpha plus pi or 180 degree, then T3 and T4 will be turned on, and therefore the output voltage now is the mirror image of the supply voltage, and that's why you have this sort of waveform for the output voltage. And again, so if you vary alpha to pi, then you can see a different area under the curve, and therefore the output voltage, the average of the output voltage will be changed, right? So as you increase alpha, if you increase the alpha value, you're going to see that your area become smaller. Okay, becomes small. For example, at this point, smaller, and therefore the output voltage, the average of the input voltage will be smaller until you have alpha equals to pi there, and you're not going to see any waveform at all because your alpha equals to pi. When alpha equals to pi, then you have a zero voltage at the output. Okay, and in terms of input current, again it will follow the output current. So if you look at the output current here, if you look at the output current, actually it copy the waveform of this output voltage, but scale down to the factor of whatever the R here, because I equals to V over R, isn't it? Right? So the current wave shape, the shape of the output current will be equal to the voltage here, output voltage, but it's scaled down by a factor of R. And therefore in the input side, you're going to see that the input will be carrying the output current, positive cycle, and then negative half cycles, it will be the opposite to the output current. Yeah, so this is the output current. Okay, right. So in terms of the derivations, so again, this always be the general equation for any waveforms, be it a single phase, three phase, any waveform. This is general equation for you to obtain the average value. You must integrate from 0 to t, one cycle, and then you divide by the period, the t, of that particular waveform. And when you look into this waveform, and therefore you must change accordingly, because now the period, it will repeat by t, isn't it? Oh, sorry, pi, right? It will repeat by pi, so that's why now you change that one to 1 over pi, and your integration now from alpha. Okay, so your integration now become from alpha to pi, right? So the rest is mathematics. So please make sure that you fill in the gap. Okay, you derive yourself start from blank page, a blank paper, you start to derive, and that can give you and get this output voltage equation. Right? The average of the output voltage equation is always V peak over pi minus cos pi plus alpha, and you will get this final equation here. Right? So this is the average value for the full wave control rectifier with purely resistive load. Purely resistive load. Right. So now let's look at the resistive and inductive load. For this particular circuit, if you have this load which consists of resistive and inductive load, there are two conditions that you need to consider. The first one is by looking at the discontinuous output current. So this is your output current. Output current will be flowing that loop, right? So this is your output current. Okay, so your output current can be in two conditions. The first one being discontinuous output current. Okay, so this is, if you refer to the waveform, this is your output current. Right, so there is a discontinuous output current whereby your output current touches zero levels. There is a zero levels here. It touches a zero level and it stay at zeros. So this is discontinuous current operation. Okay, and there are the other case is whereby we have a very large L. L here is very large. Again, because of the, if you have to think about the machines adopt motor, right? So if you drive a motor, then again the windings will result in a very large inductive, and that's why your current become continuous. So if you look at this waveform, the current now become continuous. This is your output current. Okay, so there are two conditions that you need to consider. So for the first case whereby you have small l, right? Because due to l is small, or you can have this beta in the circuit, which is beta is always referred to the extinction angle, whereby the current become zero. So this is your current. So your current becomes zero at this point, whereby you have a beta here. So that happens when your beta here, the extinction angle, is smaller than the pi plus alpha, which is the firing angle for the next couple of diagonal switches. Okay, for example, you have T3 and T4 here. So if you look again, this is where T1 and T2 is operating. So this is T1 and T2 operate, right? So T1 and T2 operating, and then during negative half cycles, okay, we see that the current is still flowing in that T1 and T2, and it dies off. It becomes zero at this beta, right? And then the thyristor 3 and thyristor 4 will wait for alpha plus pi, and then you have the voltage equation, waveform again, right? So that is the case of this continuous output current. And if you want to derive for the output voltage, you have to look carefully. So again, you apply the general equation, which is integration of 0 to t, the equation V out t dt, and you have to divide by period, the t, sorry, or in terms of radian, you're going to have VDC equals to 1 over pi. You integrate 0 to pi VDC theta d theta. Okay, so in this case, if you look carefully, there are two area, which is the first one will be that area, and the other one will be that area, isn't it? Okay, so from here, okay, this point also known as beta minus pi. Okay, so this is very similar to this firing angle, but you do minus by subtract by 180 degree, you will get this point. Okay, so now the first integration will be from 0 to beta minus pi, and this waveform actually the opposite waveform of the supply voltage, isn't it? Right, so this is only a negative of the supply voltage, so it will be V negative V of t, right? Because this waveform is V as t, so that negative waveform here actually the negative of the supply voltage. So that's why in this integral you're going to have 0 to beta minus pi minus v peak sine theta plus alpha to pi from alpha to pi, and then you have v peak sine theta, and then solve that. Now you're going to have v peak over pi cos beta minus pi plus cos alpha. Okay, so this is the case of discontinuous current operation. Okay, so what happens if you have a continuous current operation? So in this case, there is no point where current goes to 0. So therefore, beta is 0. Beta is non-existent. Beta is 0. You don't see, it doesn't exist in the circuit, right? Beta doesn't exist. And therefore, in this case, if you look at this particular operation, so let's assume that we are in that particular point whereby we have T1 and T2 operating. Okay, so T1, T2 is operating this point, T1, T2 operate, and then just after the 0 crossing to the negative half cycle, T1 and T2 still flowing. They are still flowing because there are continuous current that flowing in that output, isn't it? So there is still a current flowing at the output, forcing the thyristor 1 and thyristor 2 to stay on. Okay, until you trigger thyristor 3 and thyristor 4, because during negative half cycle, T1 and T2 is already reverse bias. Okay, it reverse bias, but because of the current still flowing in the direction of the arrow of the diode thyristors, and therefore T1, T2 keep continuing to flow to conduct the current. But once you trigger thyristor 3 and thyristor 4, then there will be a commutation of current from T1 and T2 to T3 and T4. So just after that, then it will follow the T3 and T4. So just after then, going to see T3 and T4 operate. T1 and T4 will be off. Right? So that will be your output voltage. This is output voltage whereby you have going to see that we will copy that input voltage until negative cycles, and then you continue. Right? So this is your output voltage, and therefore if you want to get the output voltage, the average of the output voltage, you're going to integrate from 0 to alpha, and then you're going to have alpha to pi. There are two integrals, right? So if you look at this note, then you can get this v minus 0 to alpha to minus v peak sine theta d theta, and then you have another integral from alpha to pi v peak sine theta. Solve for that, and you will get the equation of 2 v peak over pi cos alpha. So you have different output voltage waveform. The first one is given by this equation, all right? And in the case of continuous, you're going to have this equation. All right. So now, what happens is, so I'm going to show you some simulation here to bring this PC. Don't worry, I've already shared with you this circuit. If you go to All right, if you go to my Padlet under PC column, you're going to see a new files being uploaded here. So I've already shared with you single phase full wave control rectifier. So have a try and look at this. Try. You have to try yourself your piece using the PC, yeah, to simulate the circuits. So that will help your understanding of the power circuit operations. Okay, right. So we have this circuit. Supply voltage. Why it is 339? Because the supply voltage for PSIM requires this. If you look carefully, peak amplitude. It wants a peak amplitude. Is it? Doesn't want the RMS, but it wants a amplitude. So if you multiply 240, the RMS, with a square root 2, you will get 339.44, 0.41. You can also write in terms of square waveform. Square root, which is 240 multiplied by square root 2. Okay, you can try that. I can't remember whether you can times, or yes, it's a 240 square root 2, or you can give a value of 339.41. No problems. Okay, so now, and this is known as gating block. So 50 degree, make sure it's a 50 degree. You double click that, make sure its frequency is 50 degree. All transistors are 50 frequency of hertz, 50 hertz. And then we have a switching points, which is the firing angle of 45 and 46. So again, this is firing angle, and this is a short pulse. Okay, 45, 40 degree. So if you want to, if you don't know, if you want to get some information on this parameter, you just simply click this help. Okay, just click this help, then you'll be able to understand what is the description, what it's all about. Okay, if you want to look at this, okay, frequency. So operating frequency in hertz, you need to put in terms of hertz, not radian, no other point. Number of points, number of switching points in one period. So if you have 2 points, which is if you think about the pulse, so you need to supply 2 information, 1 point, 2 point, isn't it? Okay, so that's why you you insert number 2 here for the number of points, so that you can define these 2 points, whereby you have 45 degree and you have 46 degree for a short pulse. Okay, right. Now we have 10 millihenry. So let's try to simulate the circuit and look at what will be the output current, output voltage. So I'm going to click that, run simulation, and this is my simulation. Okay, so in this case, with L equals to 10 millihenry, the output current is discontinuous. I'm going to put in the IDC as well. Oh, no IDC. So I think I need to put in the IDC. So I'm going to remove this and then put in series the output current. Make sure that you have the dot here. The dot of the probe is actually denotes, tells you where the current flows into the ammeter. Okay, and then that, and the other one, that. I'm going to give this as a I out, I 0, the output current. Okay, so if you look at this simulation parameter, here you have this total time, whereby I'm going to simulate for how many cycles that? So 0.2. If you have 0.02, I'm going to simulate for 10 cycles. Right? I'm going to simulate for 10 cycles, and I only record for the last 2 cycles, which is I'm going to start with print time 0.16, and then you're going to have 0.18 for the first cycles, and therefore it will end at 0.2. So this define where you want to start PSIM to save the points, and you want to observe that out the last two output voltage, the last two cycles of the output voltage. Okay, right. So now try to simulate again, run simulation. Okay, going to see the output voltage, change it to 2. So that is output voltage. Now I'm going to add another probe, a scope. I'm going to look at the output current, change it to 2. So that is my output current. Okay, so therefore if you with the L equals to 10 millihenry, the output current is discontinuous, and therefore the waveform is very similar to the waveform for the first case, right? So in order for you to get the average value, you must have this alpha value as well as the beta, isn't it? And you need to have alpha and beta as well. Okay, so what about now we're going to increase the value of inductance to 100 millihenry, for example. Run again. Look at that. Now the current become continuous. Okay, so if I adjust this X, I'm going to adjust the, click here, the Y value. I'm going to start with 0. Okay, now I can see that the output current is continuous. So in that case, you're going to see that the current is the output voltage follow the second case, second condition, whereby it's continuous output voltage. Okay, right. So now if I increase more, what will happen? 1000 millihenry, for example, around the circuit. That means what can you tell me on the waveform here? It is not symmetrical, isn't it? The current is still rising. You are still, I think I make an analogy before. If you want to drive from for example, if you want to go up to the Cameron Highland or Genting Highland, you always climb the hill, isn't it? So now you are in the stage of climbing the hill. So this circuit cannot be analyzed because I stopped at 0.2. So I must actually increase the duration of time. So I must increase this value, total time. And so I'm going to add another 10 cycles. I'm going to stop at 0.4. Now I'm going to change that 0.36 to get the last two cycles. Now I'm going to simulate again. Still climbing, isn't it? So you still have a climbing current. No worries. I'm going to increase again to, let's say, 1.4, and this is going to change to 1.36. Run again. Now you have a symmetrical output current. Okay, so output current become stable now. Then you can measure, make the measurement, isn't it? So if I can change the Y again to 0, start from 0, go to see this report. Now it become ripple, less ripple, isn't it? So if I increase again this to, let's say, 5000 millihenry, run this mission again, still climbing, so I have to add another duration time, 2.36, run again, let's have a look. Okay, so it become continuous. If I can reduce Y to 0, then I can see a a ripple free or a constant current at the output. Okay, so in this case, if I look at the input side, 2.36. So if I look at the input side, I'm going to see a current. This is input current. What can you see? This is a constant current, isn't it? This is a square waveform, right? This is a square waveform, and if I can add the supply voltage, there's no supply voltage. Okay, so I'm going to add another supply voltage here. Double click that. So this is my VS supply voltage. Okay, this is the probe for supply voltage. I'm going to run again. Okay, I'm going to add the input current. So that is my input current. I'm going to change the 2.36. Okay, so if you look at this waveform, the input current is a square waveform, isn't it? But it shifted by the value of alpha. If you compare with the the supply voltage, it will be shifted to the right because it's lagging. Now the current lags. I mean, if you, in terms of waveforms, then we can say that the current lagging behind Vs supply voltage by the firing angle of alpha, isn't it? So this is your alpha. Okay, in this case, if you look into the Fourier series, the Cn, which is the harmonic contents, the amplitude of the harmonic series will be the same as the square waveform that we have before, which is Cn equals to 4IDC. So this is your IDC, isn't it? So this is your IDC. It will be 4IDC over n pi. Okay? So Cn will always be equals to 4 IDC over n pi. So if you want to find for the first harmonics, that become 4 IDC over pi. If you want to look to the third harmonics, that become 4 IDC over 3 pi. And fifth harmonics, 4 IDC over 5 pi. The amplitude is very much similar to the square waveform that we have before. But in terms of the phi n, it's a bit tricky here because it's no longer 0. The phi n, the angle of the the angle of the harmonics is no longer 0. So here we're going to see, if you refer to that particular circuit waveform here, now in this waveform we're going to have supply voltage. This is supply voltage, and then the blue waveform is your current waveform just now, and we have this. The black is actually represents the first fundamental component of IS. It will have the same frequency with the current equation, current waveform, okay? And therefore, if you measure the fundamental components, if you measure from that point to that point, you're going to give the angle of phi1. The angle of phi1 is alpha, isn't it? Okay, so that is the difference between the control rectifier and uncontrolled rectifier for full wave, single phase with highly inductive load conditions. So we're talking about highly inductive load conditions. So therefore, state here that Cn equals to the peak current, the harmonic of the square waveform before for IDC over n pi, where n equals to odd 1, 3, 5, 7. Hence the total harmonic. So you're going to have the same total harmonic distortion, 48.4%. But in terms of displacement angle, okay, however, it's no longer equals to 0 because you have the control rectifier. Now your phi1 equals to alpha. Then the displacement factor equals to cos alpha because it's cos phi1, isn't it? And then the power factor now become, so you have to substitute the displacement factor that you have before, and therefore you have is1 over is cos alpha. So that will give you the value of 0.9, and therefore the power factor actually depends on the cos alpha. Okay, so the value of alpha will actually affect the power factor. Okay, so it will not be in the case of square waveform for the uncontrolled rectifier, cos alpha equals to 1 because alpha is 0, and power factor of uncontrolled full wave rectifier with highly inductive load equals to 0.9. All right, so try to understand that. Okay, so now we're going to continue with the in the case of you have this freewheeling diode. So I hope you still remember that we put in the freewheeling diode. We insert freewheeling diode or flywheel diode because you want to remove the negative area, isn't it? Why? Because that negative area actually reduce the available output voltage. So we want to remove that negative area, and therefore you increase the amount of output voltage available for that particular rectifier. Right? So let's go back to this previous circuit whereby you don't have this freewheeling diode. Okay, so let's look at the waveform. In the case of a continuous current, now we are in the case of continuous current. So if you go back to the waveform just now, in this case, you have a negative area here, isn't it? So you always have this negative area. So this negative area actually reduce the amount of the output voltage available for the rectifier. So you want to get rid of this. You want to remove this. So how to do that? Again, we have to place the freewheeling diode across the output voltage. You're going to across the load. You're going to put in parallel, and therefore during negative half cycles, so at this point, just after that point, we still have current flowing, isn't it? Now the current will force the diode to be turned on. So instead it's flowing, the current flowing through that direction. Now it will follow this path to the freewheeling diode. So this is no longer, so therefore diode will be turned on and it will appear as a short circuit, isn't it? So when the diode is on, it will appear as short circuit, and therefore your negative area here will be removed because current voltage become 0. Okay, so therefore you have a more available output voltage. If you place the freewheeling diode in the upper, we call it in parallel with the load. Okay, so now we're going to have a resistive and inductive load with freewheeling diode as well as the back EMF in the circuit. Okay, so first we look into the output current. When you want to describe this circuit operation, look into the output current. So if you refer to the output current, it becomes discontinuous because of that back EMF. This voltage actually oppose the current, so the current flow is flowing in that direction, and we have this back EMF which is opposed to the output current I0. So that's why it forces the current to goes to 0 at that particular point, isn't it? Okay, so the current will goes to 0 at this particular point. But before that, what happened is that the current is continued to flow in the diode, right? So therefore you're going to see that again this will be short circuit, and therefore the output current, the output voltage become 0. So at the beginning, if you look at, if you refer to that the beginning here, so you have current flowing, and during this time the output voltage is 0. Okay, so but then the output current dies off. In this case, we have beta minus pi. Actually, in our previous explanation, beta is actually there, isn't it? Okay, which is the finding angle for the next pair, the next cycles. Okay, so but in the beginning, that will be beta minus pi. It's very similar point where current goes to 0. So in this case, so at the beginning, start with 0, and then when and the thyristor 1 and thyristor 2 has not been triggered yet, so T1 and T2 has not been triggered yet because you have 45 degree. It has to wait to until 45 degree to trigger T1 and T2, right? So, and therefore at this point, after the current goes to 0, there is no current flow, and the output become, so there is no, sorry, so there is no um, there is no current flow. Okay, after this beta minus pi, so there is no current flow, and therefore the voltage drop across this is 0. There's no current flow, this is 0, and therefore if you measure from that point to that point, the output voltage will be equals to 180 volt, which is the back EMF, whatever the back EMF. So at this point, going to see that the output voltage equals to 180 volt, right? And then we have alpha triggered. So just after this, you have alpha triggered here, and now the normal circuit operations whereby thyristor 1 and thyristor 2 will be turned on, and therefore the output voltage will follow the supply voltage again until negative half cycle, whereby you still have the current flowing, and it will turn on. At this point, you're going to turn on the diode again, so diode will appear as a short circuit, and therefore the output voltage become 0. And just after that, we have current goes to 0 at beta, and there will be no current flow, and therefore the output voltage become equals to 180 degree. Okay, so this is very much how to explain the circuit. So you can read this, and then again, if you want to get the average, now you have this one area here. So this is area 1, which is a rectangular. It's just a matter of you multiply the x multiplied by y, so E multiplied by alpha minus beta minus pi, if you like. Then you get this area under the curve, and the other is the integral of from alpha to pi. Okay, alpha to pi. So let's have a look. Okay, that's why you have area 1 and alpha to pi v sine theta. Solve that, and this give you the VDC equals to 1 over pi E multiplied by alpha minus beta minus pi plus the area under the integral, under the curve, and then you have V peak 1 plus cos alpha. Right? Okay, so now we're going to continue with the effect of line source inductance on current commutation for single phase full wave control rectifier. So again and again, we always have this source inductance at the front end, which may come from the transformer winding, or it can be from the cable inductance. So in practical, you always have this LS in the front end. All right, so we're going to analyze the circuit again, and we're going to assume that we have a constant current output. The L is very, very large, and we're going to replace the R plus L with a constant current IDC here. Okay, so all right, before that, if you still remember just now, we have discussed the circuit without this source inductance with the normal circuits here, okay, whereby during negative, at this point, so we have alpha at this particular point, isn't it? So this is your alpha when you trigger thyristor 1 and thyristor 2. Before that, okay, before that alpha, you're going to see that the thyristor 3 and thyristor 4 are operating. They are on, isn't it? Okay, so without the source inductance, what happens is that the current will change state instantaneously. So if you refer to the IT3, the current through the thyristor 3 will actually goes down to 0 instantaneously. It goes down 0 to instantaneously without the source inductance. We are actually discussing without the source inductance. ITT drop from the IDC, the output current, to 0 instantaneously. The word is instantaneously. It's a step change from IDC to 0. And that also happens in the current through thyristor 1. Okay, so the thyristor 1 now from 0 state, because it's turned off just now, it will change to IDC instantaneously. So there is no current overlap. There is no current overlap at all during there is no inductance. But since we have the source inductance, there will be a delay of current to change state. Right? For example, if you look at this IT3, if I may zoom, okay, the current for the thyristor 3 will start to reduce just after alpha with a certain rate until it goes to 0, and that also happens to the thyristor through T1. Thyristor 1 it start to rise from 0 to the circuit current IDC, the output current of IDC. So there is an overlap of current, isn't it? In this short of time, which is known as an overlapping period or commutation interval, during this time, you're going to see that T1 is on, T3 is also on, right? This T1 and T3 on because the current flows are still flowing in the thyristor, as well as T2 and T4. So all thyristors are conducting current during this overlap. Okay, and therefore, if you look at the output voltage, because of that, we said just now that all diodes in on during that interval, commutation interval. So all thyristors are on. This will appear as a short circuit, and if you measure the output current, across that, you're going to see a short circuit, isn't it? And therefore the output voltage becomes 0. So that's why during the overlap overlap period or the commutation interval, you're going to see that the output is 0. Yeah? So just now, without the source inductance, your output voltage actually becomes this, isn't it? If you refer back to your waveform just now, without the source inductance, you have this waveform, and because of that source inductance, now there is a missing area. So there is a missing area during that overlap period. Okay, all right. So in solving to analyze the circuit, we're going to start with looking at what will be the equation for U, the overlap angle. Okay, we're going to find what is U, and then we're going to also to look into the output voltage equation to describe the output voltage equation, the average output voltage equation for for voltage equation. Okay, right. So let's start with the this equivalent circuit during overlap. So during overlap, we're going to consider this circuit, this loop, we just focus on this particular loop whereby you have this loop, right? So only focus on that particular loop. Okay, and we're going to see that this is short circuit. Tester 1 is on, tester 3 also on, and you have current IT1 here, and you have IT3 on, and as well as you have a constant current at the output. So this is constant current I DC or I naught. In this example, you have the value is 10 amp. Okay, value of 10 amp. So that will be the equivalent circuit that we in the node. Let's go back. Okay, so this is the equivalent circuit during overlap. So you have the supply voltage and only the L. So equivalent circuit during overlap. So take the KVL, then you have Vs equals to VL, definitely, and then you convert that into radian. While converting that into radian, you're going to see that V peak sine theta now become Ls omega, right? Because of that conversion, you have an extra omega in the circuits here. Now it becomes di over d theta. It's no longer di over dt, so it becomes di over d theta. And to obtain the overlapping angle interval, you integrate both sides. So you integrate both sides, right? And the integral, the limit will be alpha to alpha plus u. And for the input current, look at the input current. Where is it? So this is your input current. Okay, so this is input current. The limit is from minus IDC. Look at that, minus IDC to IDC, right? So that's why the limit is from minus IDC to IDC omega s di, right? So for that, and you will get this equation. The overlap angle mu equals to cos inverse cos alpha minus 2 omega ls IDC divided by V peak s minus alpha. And again, to make it, I mean, to be not for my advice is always treat this in radian. Everything should be in radian. So this need to be converted into radian, right? And when you solve, your mode of your calculator should be also should be in radian, right? Don't mix up. Sometimes you're going to use 180 degree. No, you cannot use degree here. Okay, do not use degree here. Okay, you cannot use degree here. You must convert that into radian in solving the equation for u. Okay, and next is to get the average of the output voltage. So what we can do is, again, we know the equation for the output voltage, the average of the output voltage without the source inductance. So without the source inductance, so this is your voltage waveform. Sorry, and we also know the equation for that from the section before. We have this in this section, isn't it? 5.3.2. And therefore you only need to find what is the missing area here. You need to find the average voltage drop of the missing area here, and then you just subtract the equation that you obtained before from this section with this missing area, and that will give you the output voltage, the average of the output voltage for with the source inductance, right? Magnified waveform during wave overlap, and then okay, so you have V drop. So if you integrate, then you have you need to integrate that, so it becomes alpha to alpha plus mu. Okay, so you integrate from alpha to alpha mu, and the same V peak sine theta. Okay, and if you refer to the equation 5.13, so they are the same equation, right? And then you don't have to solve for this. Just use whatever you have in the 5.13 just now, and therefore V drop equals to 2 omega ls IDC. And again, since the output voltage represents since the output voltage repeats by pi, the average voltage drop becomes I think I have changed. I've just a matter of I did not update. I haven't updated my notes here. So this is area. Okay, this is area, and then this is the V drop, the average voltage drop. So this become a V drop, no hat, just a V drop. Okay, and finally you have the output voltage become VDC equals to 2 V peak over pi cos alpha minus 2 omega ls IDC. Right? So very much the effect of source inductance, and therefore you have two effect of having that source inductance. The first one will be a reduction in the average output voltage because you have the missing area there, reduction in the average output voltage VDC. And as what we did for before for single phase half wave rectifier, there is a distortion on the voltage supply of the converter. Okay, the distortion on the voltage supply of the converter at the point of common coupling. So if you refer back to your supply voltage, this is your supply voltage, and at the point of PCC, you can refer to the previous note on the PCC. So at the point of PCC, you're going to see a distortion of the output of the input current. So if you have several loads connected to the same point, then the other load, load 2, load 3, will see a distorted input voltage. The supply is no longer sinusoidal, so there will be problems related to harmonics. All right. Okay, the last section of this chapter 5 will be the inverter operation. So we know that the rectifier is actually from AC to DC. The power flow is always from the AC to DC, isn't it? But in the case of this control rectifier, at certain condition, we also have this power flow from DC back to the AC, and that very much because of the output voltage, the polarity of the output voltage. Okay, so let's consider these two circuits. Now we're going also to assume that we have a constant current at the output, right? So we have a constant current that flow in this direction. Okay, in that direction, moving downwards, and that is your output current because of we driving a motor, as what we discussed before, right? So if you have your alpha, which is in between 0 to 90 degree, okay, you're going to see that the average output voltage is always positive value because you have more volt area in the positive area compared to the negative area here. Okay, and therefore if you take the average, then you become a positive output voltage, right? For example, in this example here, we have alpha equals to 60 degree, and you will get the V output, the DC output voltage become 108 voltage, 108 voltage. Okay, for 0 to 90 degree, you're going to see that a positive output voltage, and and therefore the polarity will be plus minus. Okay, you're going to have your polarity of the output voltage will always be plus minus. And if you look at the conventions, in any conventions, if the current flows into the positive terminal of an element, and that will be the load. For example, if you have the resistor, right? So resistor is always a load. So that's why for the current, the polarity will be the voltage of the voltage across VR will always be positive and negative, because, and if you look at the current flow, it will enter the element through positive terminal. and that becomes a load, and therefore we have the current flow or the power flow from AC to DC. However, if you have in the case of alpha from 90 degree to 180 degree, if you look at the waveform now, you have more negative area here. You have more negative area compared to positive area. In this case, if you measure or if you calculate, you will get a negative output voltage, negative 108 volt with alpha equals to 120 degrees. So in this case, your polarity of your output voltage will change. Okay, the polarity of your output voltage now become plus and minus, isn't it? It become plus minus. Sorry for uh, the arrow there. So it become plus and minus there. In this case, we're going to see that the current leave, Leavs. So the current leaves through positive terminal. Okay, so that now in that convention we have that DC side will become the supply, become the source of the power flow. So now the current flow is actually from DC to AC. So if you can think about the supply voltage, okay, if you have a supply voltage here, plus minus, right? So in this case, your current always leave with a positive terminal, isn't it? So that is your supply side. Okay, so in when you have alpha in between 90 and 180 degree, your output voltage is will be a reverse polarity, so it become plus and minus. Now your current actually leaves from positive terminal. Okay, it leaves from, so this become source and that become the load, and the power flow is actually from DC side to the AC side. So we can relate that into the quadrant of the rectifier operations. So if you look at this, because it's 4 quadrant operations, okay, we can draw with the axis of VDC for y-axis, and we have the current IDC as the x-axis. So in this case, we have both positive value. You have positive VDC and positive current. So in this case, you have first quadrant whereby you have a rectifier operation. But when your alpha becomes 90 degree, sets to 90 degree and be in between 90 to 180 degree, your voltage is negative. And this case, the rectifier now operating as inverter. So it operates in under inverter operations. And this is known as fourth quadrant inverter operations. And this quadrant actually always normally we refer to the motor operations, right? And this is very important, and we discuss on the rectifier, the control rectifier with a constant current output. Okay, thank you very much.